This talk is actually interplanetary networking. At least that's what I like to call it. I think it's delay-tolerant networking is the official term. But it's a little bit different. I don't think we've ever had a talk like this at Netdev. This is where we're talking real distances. So if you consider networking to Mars, that's like 225 million kilometers, I believe. So a little bit different, extreme. We like that at Netdev, of course. And the thing is, the problem that Fred and Rachel are going to be talking about today, we've seen them before in some sense. We're going to be talking about MTU. Obviously, with distance becomes latency. This is where we find out the speed of light's actually pretty slow. But also, I think there's a lot of forward error correction and some other techniques. So with that, Fred and Rachel.
Hello. Hi. So I'm Rachel Dudukovich from NASA Glenn Research Center. And so I'm starting off introducing our talk with some of the use cases that we're looking at with NASA for delay tolerant networking. So our project is, so not only are we delay tolerant, we're high rate delay tolerant. And so we recently completed testing on board the ISS with our HDTN software. And in this case, we were kind of looking at actually a large scale system in terms of space. So this was running actually on a commercial laptop that was on board the ISS. And we had a laser link is kind of what we're focused on. So there's a project that's called Illuma-T and LCRD, and they were doing, that's a laser relay communication demonstration. And those were run by NASA Goddard. They were focused on doing a demonstration of gigabit per second data rates from the ISS. So it had 1.2 gigabits down to Earth and 155 megabits up to the ISS. And also just the way some of the electronics of the Illuma-T optical terminal, it actually had a significant round trip time of 4 seconds, which is actually longer than the moon, but it's just a case of how all of the encoding and all of the various layers that it had to go through of the space networking protocols gave it this long round trip time. And so there's protocols that we've developed specifically for that. The system also, the network of the ISS has science payloads. So it kind of has a network in itself on board ISS. So there'd be science missions, and they would feed into our high rate DTN gateway. And then that gateway goes down to these multiple ground stations. So this little animation has that. So Goddard actually had 3 different ground stations. And we also ourselves, NASA Glenn, has a PC-12 aircraft. So we completed this internetworking demonstration where we had our HDTN gateway on board ISS. We sent the laser link from Illuma-T to LCRD. LCRD sent it down to the ground network. And then from the ground network, we jumped around through some of the near space network ground nodes as well as AWS. And we were able to uplink the data to our plane that was flying around Lake Erie. And that also had some of its own disruptions that while the plane was, just in the aero level, even when there's clouds and things, that causes disruptions. And so we have a couple of protocols that are specific to that. So where I have this BP, that's bundle protocol, and the bundle is the protocol data unit of DTN. And it's similar to a packet, but it's actually an overlay network. So it can have a bundle. That bundle can be on top of UDP. It can be on top of specific space networking protocols like AOS and space packet protocol also. And we actually, so below the bundle protocol, we use what's called Licklider transmission protocol. And that actually gives us reliability. So it's kind of similar if you want to think of it like TCP, where you're doing something where you have acknowledgments, except it's made to handle the delays of the space environment. So it uses it calls it one-way light time, which it measures the distance between, say, the Earth and the moon. That's the one-way light time in light seconds. So LTP has a lot of timers that while it's waiting for acknowledgments, it's using that one-way light time. And so we demonstrated a couple of things. We demonstrated an older version of bundle protocol, a newer version that also had security enabled, and we also demonstrated multimedia streaming. We also have another kind of opposite use case, which is, a very small constrained platform. And so this is a CubeSat that we recently flew that has HDTN on it also. And this is a small platform, and something that's unique about it also is the way the radio link is. So we just have an S-band radio, and it only has transmission down to the ground. And we have a short burst command interface via Iridium. And these are very small packets that are only like 200 bytes. So we can send data down S-band, and we just have a very small periodic command interface. And we didn't want to send acknowledgments over the command. So what we did for that is we're doing an experiment with forward error correction so that we can have reliability using that and avoid having the retransmissions that are caused by LTP that's used for reliability. And in this case, also, it has a very custom pipeline where this CubeSat was developed by AIM, so they have their own radio and flight software platform, and we kind of have a custom pipeline that implements some of the space protocols like CCS, GS, NCAP, and AOS transfer frames, and that feeds into AWS ground station and into our own network at GRC. So this is the HDTN architecture. It's a modular architecture, and we have a couple processes that kind of decode the bundle. So data comes into ingress, it looks at some of the headers in the bundle, and it determines what it's going to do with it. It kind of determines the routing based on its specific headers. And if the link is not available, say if it's a case where we're over clouds or we can't see the ground station, all of that data goes to storage. And we have a little plan, it's a schedule basically that we call the contact plan, where we look to see if the link is available, I'm going to go ahead and take my data out of storage and send it out of the egress. And they basically call that store and forward. So HDTN is focused on performance. So we avoid semaphores and mutex locks on shared memory. So there's no blocking or locking, it's all asynchronous processing, and we avoid copying memory. We also use platform independent dependencies. So all the message bus that we have is based on 0MQ, and we use Boost for the asynchronous IO library. And we also support a graphical interface, API, and command line interface. So we've evaluated LTP in multiple environments. We also have a software-defined radio lab at GRC, where we've done testing with LTP over a cesium Astro radio, so that's also a flight-like radio. And we've had our testing with LCRD. We also have a small test bed that emulates what's the future lunar network is called LunaNet. And so that has multiple nodes set up for something where you'd have like a rover and then going to a lunar relay and going to Earth, and it has the delays of the lunar environment. And we also have our PC-12 optical experiment on the plane. And then Fred is going to talk about testing that he did at Boeing with a very high rate test bed. So LTP has challenges. This picture is the configuration file that we use to configure LTP. And you can see it has a lot of parameters. And so this is prone to error. A lot of people have difficulty understanding what do these parameters mean. And when they're not tuned properly, they can actually have very poor performance. So there's really some room to improve it. And it also still relies on two-way communication, which in the case I was discussing with the CubeSat, that may not be possible. Or it may be the case that when the link is very asymmetric, since you're waiting for those responses, it really can degrade the performance even if you have a very fast link. So we're looking at some parameterized benchmarking analysis, trade studies between LTP and what they call custody transfer as part of bundle protocol. And we're looking into some new protocols that are being developed by ESA that's called high performance reliability protocol, and also forward error correction. And now I turn it over to Fred.
Okay, thank you, Rachel. So I have done some work on performance evaluation of some DTN implementations, HDTN, and a second one called ION, which stands for Interplanetary Overlay Network. But the first thing I got into is I noticed that there were some problems with the packet size issues. The LTP protocol encapsulates LTP segments and UDP IP packets. Most internet and DTN links configure a 1500 byte maximum transmission unit, which is the largest size packet for the link. The smallest link in the MTU in the path determines the path MTU. Transport layer protocols like TCP, QUIC, and LTP often limit the packet size to no larger than the path MTU. And if you go larger than the path MTU, then what you end up doing is invoking IP fragmentation. But we've seen these studies that say that IP fragmentation is considered harmful from back in 1987. And the newer IETF draft, IP fragmentation considered fragile, is still claiming in 2020 that fragmentation has issues. So the best current practice that we see in the IETF is to use path MTU discovery instead of IP fragmentation. And we've got 2 RFCs on how to do path MTU discovery in IP. So the problem with path MTU discovery is it depends on ICMP packet too big messages from the network, and they can be either lost or spoofed. So we can't rely on getting the path MTU discovery messages that we need. Packet too bigs always indicate packet loss. The source has to back off to using smaller packets for long periods of time before trying again, and that's not adaptive. Discovering larger MTUs over arbitrary internet paths is difficult using legacy path MTU discovery mechanisms, but thankfully, there are some newer packetization layer active probing approaches that have been published in the IETF, and there's a new approach that uses passive hop-by-hop measurements, RFC 9268. So generic segment and receive offload, the path MTU discovery shortcomings often cause transport protocols. Oh, okay, what do we do? Oh, we're back again, okay. Path MTU discovery shortcomings often cause transport protocols to use small segment sizes. And small segment sizes can cause a performance bottleneck at the operating system call interface, since only a small amount of data is copied per system call. So GSO GRO concatenates multiple smaller segments into a larger buffer to amortize the data copy across the system call interface. The source operating system then fragments the large GSO buffer into smaller whole packets for transmission, and the destination operating system reassembles the packets into a larger GRO buffer for transport protocol delivery. Now let's talk about the delay-tolerant networking protocol layering. DTN introduces a new layer called the bundle protocol. It's a new layer in the architecture that's below the applications, but above the transport layer. The Licklighted transmission protocol is a transport protocol convergence layer for the bundle protocol. Just a moment. Oh. So the LTP is a transport layer protocol convergence layer for BP, and you can see the layering here in the stack over on the left-hand side, with BP below the applications and LTP as a convergence layer adapter. LTP breaks bundles into segments for transmission, and we have found that the segment size affects performance. Now, the other DTN implementation I referred to called ION uses a semaphore-based method for enqueuing segments for transmission. So this LTP meter process is a lightweight process that initializes the session buffer and gives the buffer open semaphore. The session buffer becomes filled with the bundle. Then LTP meter breaks it into segments and gives a segment enqueued semaphore for lower layers to consume the segments. This is in contrast to the way the HDTN architecture is done. So the LTP performance, we tried implementing GSO GRO in the ION DTN LTP, but we saw no performance benefit. So we figured that the system call interface was not the bottleneck for ION. Experiments with larger ION LTP segment sizes showed dramatic performance increases, even when IP fragmentation was engaged. We also saw that larger HDTN LTP segment sizes also showed significant increases. So for 2 popular DTN LTP implementations, increasing the LTP segment size directly increased performance even when IP fragmentation was engaged. And that kind of harkens back to the early days of internetworking when we had NFS over UDP that saw greater performance using larger segment sizes with IP fragmentation. The performance test bed that we used was really kind of modest in comparison to some of those we've heard about here today. We had Dell Precision 3660 workstations running Ubuntu, 12th generation Intel Core i7 processors with 32 gigabits memory, and the NICs that we used were Intel E810 100 gigabit per second Ethernet network interface cards. We simply connected the two of the cards back to back with the Cat6 Ethernet cable. The NICs are able to accept MTU configurations up to 9702 octets. And the sizes we used for testing were 1500, 4500, and 9702 octets. So with the NICs set to a 1500 MTU, with HTTN, we saw that by sending a segment size of 1400 bytes, we were getting a performance of 9 gigabits per second. Now that's the magenta curve that you see here. The green and the blue curves are iPerf3 using TCP in the blue curve and UDP in the green curve. So when we boosted the segment size, though, to 16K bytes, we got all the way up to 18.125 gigabits per second. So that's a 99% increase by going to the larger segment size. And then out to the far right, when we bumped the segment size up to 64K, we got a 127% increase up to 20.6 gigabits per second. Now this is using IP fragmentation, which is kind of surprising because we're sending packets larger than the path MTU. IP fragmentation is breaking them into fragments and giving us better performance. Now, I want to say also that we didn't get a chance to try GSO GRO with HTTN. My feeling, based on what I'm seeing in these charts, is that we would probably get similar performance using GSO GRO as what we're getting with IP fragmentation. The difference being that with IP fragmentation, you don't send as many segment headers. And so you get some gain by not sending the segment headers. But we'll talk more about that in a little bit. So then when we boosted the MTU to 4500 bytes, we saw that at 4400 byte segment sizes, we got all the way up to 20 gigabits per second with HTTN. That's quite a significant increase over the 1500 byte MTU. When we boosted the segment size to 16K, we got up to 25.8 gigabits per second for a 27% increase. And when we boosted up to 64K bytes, we got 27.9 gigabit per second for a 37% increase. And then finally, we put the MTU up to 9702 octets. And for a 9600 byte segment, HTTN got 29.036 gigabits per second. And by increasing to larger segment sizes, we saw a very minor increase in comparison, again, with IP fragmentation engaged. And the increase that we're seeing is likely due to the fact that we're just sending fewer segment headers with IP fragmentation. So what we've seen with HTTN performance is that it engages the network at high utilization, which makes it what we think to be a good fit for high data rate DTN relays over laser links. For nominal path MTUs like 1500 bytes, performance is more than double with larger LTP segment sizes that engage IP fragmentation. And then for larger path MTUs, larger LTP segment sizes provide significant performance gains. IP fragmentation still provides considerable gains for larger packet sizes. So that means that HTTN might benefit from jumbo path MTUs larger than 9702. HTTN may also benefit from GSR GRO that's to be investigated in later phases of our investigation. Then we looked at ION, the Interplanetary Overlay Network Protocol, and we saw a very different performance profile. We found that whatever MTU we set the cards to did not make any difference at all for the ION performance. So that means it's not the network that's causing us the problems with ION. So at low segment sizes like 1400 bytes, we were only getting 154 megabits per second out of ION. When we increased to 16K, we get up to 1293 megabits per second. And when we increase to 64K, we get 3877 megabits per second, which is a factor of 25 greater. So in other words, with the increasing segment sizes, we see linear increase in performance based on just increasing the segment size. So that means that ION DTN is not really fully engaged in the network at nominal segment sizes, but it's based on a lightweight multiprocessing architecture, and that makes it a good fit for low-end links and end systems such as spacecraft, low-end systems like spacecraft. Performance profile is identical at all path MTUs. Increasing the LTP segment size produces a linear performance gain for all sizes when IP fragmentation is fully engaged. So we know that with IP fragmentation, the maximum segment size that you can use is 64K bytes. But we think that significant ION performance gains would be likely using super jumbo segment sizes that are larger than that size. 256K bytes, 512K bytes, a megabyte, 10 megabytes. We're talking about true jumbo frames at this point. And the ironic thing is that this is for low-end systems. We're seeing that larger packets make a lot of sense. So some problems with IP fragmentation. For IPv4, you have only a 16-bit identification field that can wrap with reassembly errors possible even at moderate data rates. IP version 6 includes a 32-bit identification field, but that length is still too small if the starting sequence number resets frequently. We've been looking at devising a new IPv6 extended fragment header, and we have a draft in the IETF about this that includes a 64-bit identification field that addresses these issues. And that's going to be used by something called the Omni interface, which is an adaptation layer interface that sits below the IP layer, and I'll talk more about that in a bit. IP fragmentation is only used for segment size up to 64 KB. Larger segment sizes would require IP parcels or advanced jumbos, which again we have an IETF draft on. Now, dealing with fragment loss and reassembly congestion, if the destination can send a fragmentation report soft error to the source can adaptively increase or decrease the size of the packets it sends. That would support an adaptive packet sizing on a per flow granularity and allow for an adaptive behavior of adjusting packet sizes. Now, adaptation layer fragmentation. This Omni interface I talked about exposes an entry point into the adaptation layer at a layer below IP. The Omni interface can set an unlimited MTU, and that's the size that will be exposed to IP. But inside the Omni interface, encapsulation and fragmentation can occur at a layer below IP to make sure the packet sizes of all sizes get through. That means that the IP layer would see a stable interface that accepts larger packets, and surrogate Omni interface developed and tested in Linux kernel performance evaluation for HDTN and ION are in progress. And what about these IP parcels and advanced jumbos? So some transport protocols may benefit from segment sizes that exceed 64 KB. So peers can use IP parcels and advanced jumbos over paths to support them. Well, how large can they be? IP parcels can be 64 kilobyte segments up to 4 megabytes total. And advanced jumbos can include a single segment up to 4 gigabytes. Well, if you're sending these things that are so large, what about integrity? Well, we know that for Ethernet, the link layer CRC32 is only used for data sets up to about 9 KB. So if we use the link layer CRC for only the headers, then we can include a much stronger end-to-end integrity check and only check the integrity of the packet at the final destination instead of hop by hop. And what if corruption occurs in the path? We include forward error corruption where the sender encodes and the receiver decodes the forward error correction coded packet. And the end-to-end integrity check would then determine whether the FTC was successful. And what's great about that is that if we can get more packets to be accepted after forward error correction is applied, that means there's fewer to be retransmitted. Segment size considerations. The segment size determines the retransmission unit. Loss of a single fragment requires retransmission of the whole segment. So GSR and GRO employ MTU size segments even if the path MTU is small, where loss of a single GSO packet requires retransmission of only a single packet. So with fragmentation, if you send big and lose, you lose big. With GSO GRO, if you send big and lose, you lose only a small packet, and you can only have to retransmit that small bit that's been lost. The pragmatic approach is to use large segments only when the loss probability is small, use FCC to repair damaged segments whenever possible, and to be adaptive to accommodate change in network conditions.
Fred?
Yes.
We don't have a lot of time, but I was wondering if you could wrap it up so we could have a couple questions.
Yes. Let me see where I'm at. I think we just think now, this is the last chart we have. So future work, did you want to talk to this? Okay. So future work, evaluate TAS 11 results, LTP analysis in Glenn Research and Boeing Labs, LT parameter tuning on PC12 network experience, investigate high performance reliability protocol, custody transfer versus LTP. We want to experiment with adaptation layer fragmentation on HDTN and ION, experiment with send them message, receive them message, and GSO, GRO, and HDTN, and then incorporate forward error correction in larger packet size. And then I'll just give this as the team that was involved in the work. And there is an article that's on the web that you can look at if you're interested on this APNIC blog. And that's it.
you, Tom. Very good an interesting presentation. It might be useful for folks in this room and generally folks who are not space nerds, i.e. you two, to do some sort of phase space representation about what you care about, because depending on your use cases of whether you want to transfer lots of information in one general direction so you don't really care about the acknowledgements for things versus you do care about that for the data loss rate and your error loss expectations. So we're talking like 10 to the minus 3 or 10 to the minus 15, because those things, those changes make very deep changes in the way your algorithms would work. So we don't understand, well, I don't, I'm guessing most people here don't understand the dimensions of the problem space that you're working in, or where you are in that sort of how you want to get data from one place to another in, what do you care about type of things. Does that make any sense?
Oh, yeah, it makes a lot of sense. I make a comment like from Earth to Mars, on a good day, the one-way light time is 4 minutes from Earth to Mars. So retransmissions at that kind of a delay are really almost out of the question. So you've got to make sure that the data you send is not going to be lost due to corruption or something like that. That's where the forward error correction comes in.
So if you were doing something like that and you had more bandwidth and you were willing to throw, you might just scatter things all over the place and hope to do some, not necessarily, your definite, that it's not clear we're even understanding what you mean by forward error correction, because in my definition of forward error correction was put something into some other packet down the line and just do it this way, right? There is essentially an idea of using multiple scatter type of models to do error correction by simultaneous delivery over different channels. There's lots of different ways one could talk about this. And I'm guessing that we don't have enough understanding of what you're thinking about to even provide you with any useful feedback about, did you think of this? Is my guess.
That's a good point.
So that's exactly the reason why I want them to become involved, right? Because Linux community doesn't know any of this. But I also like the fact, so the GRO, GSO, we have a specific protocol they can test in a lab, and the conclusion right now is that GRO, GSO doesn't help. Obvious question for this community, well, why not? I mean, normally we would expect it to. Ironically, we had very similar numbers presented earlier today. You increase MTU, you can increase throughput. You use GRO, GSO, you increase throughput. One of my comments, though, was there's a big difference, because when you're doing GRO, GSO, it is an opportunistic optimization. So packet loss and congestion window shrinkage can actually mitigate the benefits of it. For MTU increases, it's a lot harder. Now, the interesting thing is when you're doing fragmentation, that's like a pseudo artificial way to increase the MTU. Kind of a bit of a lie, right? So if I make my fragment size 10 MTU size packet to TCP, one segment is 10x the normal size. So in a sense, people have tried this. It's kind of like cheating. But of course, the downside is when you fragment, you lose one fragment, you've lost the whole train. So I would say that the GRO GSO problem, that might be something that, I don't see Alex or some of our experts on this. Maybe Willem might have some expertise in it. We do have experts on this, especially the UDP, GSO, GRO. You might want to sync up with them. So if we can identify a specific problem like the GRO GSO, maybe that's a good starting point. But I agree. So in the end of the day, yeah, there's probably a whole bunch of characteristics we'd want to consider.
Thanks. Yeah. So kind of was my point too. I first want to say though, this is a very interesting domain about which we know very little. So I quickly looked up LTP, and it has all kind of. I was like, this is very interesting. Why do you have a plan to be like closer to the kind of protocols the rest of us know? And I looked very quickly at LTP. I was like, no, I understand why this is so different. So that in itself, I think, would be a very interesting talk to this community. Like, dealing with things that are only temporarily available and so. On the fragmentation versus segmentation, I have no technical reason why your sort of CPU efficiency and as a result of this, your throughput would be better with IP fragmentation on the Linux stack for UDP than with segmentation. Separately, there's whether either of these features can be hardware offloaded. I don't know for the Intel i8-10 which of the two, if any. But yeah, I believe that that's a perfect starting point for us to understand. I don't think there's a reason fragmentation would work better for you. Maybe one last point is, I don't know, since it's such a different space, what the link layers are that you're dealing with. So what your MTU limitations really are. They're also really different from Ethernet.
i8-10 does GSO, but not the hardware GRO equivalent. So there's none. I don't know if that's what is making a difference here or not, but yeah. Yeah, don't lump them together. Only the first one is available in the hardware.
Oh, I see. Okay. Yeah.
So it wasn't clear from the slides if you're aware of this, but IP fragmentation at high rate basically falls flat as soon as you see even one packet get lost.
Right. If you bet big, you lose big. So you want to make sure you bet big only when you're sure not to lose.
No, it's not even that you lose big. A single packet, like a single IP fragment getting lost, can basically burn that IP identifier forever. And a second packet can burn a second IP identifier, and et cetera, and eventually you end up with just all traffic arriving corrupted.
That's RFC 4963 that talks about that. Yeah, I've got that in my charts earlier. Okay, thanks.
And another comment is, I think you'd probably see, or maybe you'd see more help from the community if you could characterize the behavior of these networks or the behavior of the connections in terms of like the packet loss and the MTU sizes and the delays, kind of like we have the NetEM TC module to introduce delay and jitter and packet loss. Maybe, a similar, maybe just the parameters to provide to NetEM to simulate a satellite link or to simulate a Mars link or something like that, or maybe a device driver that implements something like that. Because for people that don't know how these networks work, it's impossible to do any tuning or anything like that.
Good point. Yeah, we needed to get out of here. You want to make one last comment?
At the risk of this being a very stupid question, I think it's an improvement for the slides. It is very non-obvious to me why the generic IP is below your specific to the use case LTP ion protocols, as opposed to this being the other way around, with IP being carried inside of your specialized protocols. There's probably a good reason for that. I don't know what that reason is.
LTP is really analogous to TCP, except it's made for longer delays.
So wouldn't it make sense to put something below IP that can handle your link characteristics?
So there is another group that's called CCSDS that defines a link layer framing for these space communication links. And you can run LTP directly over the link layer framing as opposed to running it over IP at all. So we looked at the performance in the case of an IP network, but LTP runs fine over just link layer framing.
I think we need to cut it. So, yeah, thanks. Very interesting topic. Okay. See everyone tomorrow. Final day. Thank you.